Welcome back. I thought it was worthwhile for us to get a little bit more experience together with pointers, both a couple different use cases of pointers and then a slightly different example that uses, as we've talked about, pointers to pointers in a practical way. First off, in terms of another way we can use pointers, it's not as common as the other examples we've already seen, but you can have and see pointers to functions. And the idea is that the function name itself can then become an input to a program. There's not a lot of circumstances in which we typically would want to do that. I mean, there are, but not the kind you would see in an academic setting. But one such example that we do see is using the so-called qsort function. So the standard C library provides a qsort. It doesn't stand for quick sort, but people call it that, which can be configured to sort an arbitrary data type in an arbitrary way, which is a very powerful thing. You get to define both what data types it's going to accept for your array, as well as what less than, greater than, and equal means for your function. So think about that's pretty powerful, right? We think of less than and greater than as being this kind of numeric concept, and it can be for our bubble sorts and the like, but it also doesn't have to be. And with this Q sort allows us, as part of the sorting, you tell it what function you would like to use to actually compare things to each other, and it'll do the actual then sorting for you. The syntax is a little complicated for that reason because it has these arbitrary array types, so there's a lot of pointers going on there. And then the syntax to provide a function pointer itself as an input to this other function is also a little messy. We can briefly look at it. I think you'll be well served by just kind of looking at this example and understanding how it works. But the syntax for it is you do provide a pointer to the array that's going to be sorted, the number of elements in that array. That's what we've been calling that length, but count is perfectly valid way. And then separately, how big in bytes is each element in the array? And when you're working with pointers, as we've talked about, sometimes you do need to know that. And then it's that final fourth input that's kind of messy here, where that's an actual pointer to a function that itself is going to return an integer value saying, is the result less than, greater than, or equal when comparing two arbitrary things? It's just a little ugly for that reason, because we have to specify. We don't know what those types are, but given two types, a pointer to two things that are two different, or same type, but two different values in an array, for whatever your definition is one greater than, less than, or equal to each other? We can use then qsort to just implement a regular sort, but that's kind of boring. Or we can use it for all sorts of other things as well. And the example I want us to take on as a programming exercise here is to sort the dictionary by length. So longest words first, shortest words last. And I'm not saying this is going to be an easy task for us, but what I'm hoping for you is that certainly when we started the semester, my guess is if I put that task in front of you, how do I sort the dictionary longest words to shortest words? You'd kind of throw up your hands and say, well, I have no idea what to do for this particular problem. And while it's not obvious, this is not a trivial piece of code we'll be writing, it's not easy, fine. But at least I'm hoping that you can start to think about, okay, what does it mean to have a dictionary? Probably a file. What does it need to actually get the dictionary into a form we can read? Well, we need some array to store these words that are in the dictionary. What does it mean to then sort the dictionary by length? Well, that's the new part that we're going to be covering here. How do I use this qsort function to sort by length versus to sort by some numeric value corresponding to integers or whatnot? So while the solution is never going to be obvious for an interesting programming problem, that's my hope for you, that thought process that we follow is something that allows you to at least think about what questions to ask and what steps to kind of break it down into. And then we're learning some new things with this example, some new library functions. The syntax is going to be a little weird, a little bit more difficult. But that's my hope for you, that you've gotten to the point where you're not just conceptually starting from zero, that you know there's a problem to get broken down, and that our data and our variables matter quite a bit. And the rest is just understanding C syntax and some of the semantics of working with these functions. Let's try sorting the dictionary. Again, a task that I'm thinking maybe you would have thought was, kind of an infeasible thing to do in some lines of code. In practice, at least with this qsort function, which is doing some of the heavy lifting for us, it's not all that bad. So this is not any starter code I have here. You can't actually see it. This is just the qsort function, just kind of a description of what that syntax is. Again, just as kind of a pointer to what we're going to have to work with here. So I just leave that there so we have it handy so we don't have to go to this link again, which that link takes a little while to read anyway. Normally we'd have it with um, multiple tabs open or whatnot and multiple things open here. So our programming exercise is to sort the dictionary by length, longest words to words, and breaking it down into tasks. We know there's an actual dictionary, so load the dictionary file. That's step one, right? Store an array of the words. We've done that before. Let's do it with dynamic memory allocation, and then have qsort do the heavy lifting. Tell qsort to sort by length somehow via that comparison function, right? Define a comparison function that does so. That's our task, right? That's what we have to implement for this program that we have here. I have several dictionary files. Short list is fine. .text, and it's good to know it. Okay, it's a nice short list of things we can sort. The thought being, if you get it to work with short list.text, it should work with the whole dictionary, which might crash my web browser here. So we're not sorting by some numeric value. We're just sorting by the length. So longest to shortest, 13 should show up. And then we have our 11 and 12 followed by those next shortest values that we have here. So let's give it a go. So those are our steps we have to follow. We have to load the dictionary file. And again, while sometimes I make it look like, oh, this is so easy, I'm just kind of typing up code as we go here, you're getting to that point. It's just a matter of having done it enough time that you have kind of the muscle memory of what you need to do to be able to load things. So we need to actually read that file. So let's be bad programmers and just assume we know that file exists. It'll just crash if that file doesn't exist. So we know that that file data type is a special pointer for handling files. We're going to read it in here. We then need to have an array to store the individual words here. Let's not do everything as dynamic memory allocation. Let's just make sure we know that there's a certain length of our words in the dictionary. That each word is at least going to be just 64 characters or fewer. And we can have a single array to store the current word that is getting written here. And then we need to have some data type. So let's make sure we're organized here. So let's say the order in which we do this doesn't really matter, but let's say add back our comments here. Load the dictionary file. Store an array of the words. In the past, we've kind of cheated a little bit, right? Where instead of we do words of max word count, max word length, or something like that. But that didn't format quite right in the first place. We call that not cheating exactly, but that is all static memory allocation, right? Where we can say if we know the actual bounds of the problem, we can statically allocate the entire array associated with it. But let's use pointers. That's what they're there for. This is a two-dimensional array, right? We have a set of words, and then we have a number of those words. That would be corresponding to our two-dimensional array. Car, star, words here. Let's initialize it to a null pointer. And we're probably going to need to keep track of how many words we have in the dictionary. So step one is really, read the dictionary. Store into array words. We've used fgetS, we've used fscanf. We've tried just a few different approaches for how to determine that we're done with our input. Fscanf is fine. We're going to fscanf our in file. If we look at our dictionary file, that was the example we had here. Fscanf should be okay because it's just one word per line and nothing else we have to kind of parse out here. So fscanf should be okay. While fscanf in file s into that individual word value, keep doing it while we keep getting a result back out, basically. We've read a valid word. It's stored in Word. We know we have at least that many more words. We can do words plus plus. Now we have to allocate our memory for the words. How many words do we have? Well, we actually really don't know. But for that big array we have here, we know it's at least one more. This is a little inefficient. We could allocate using malloc a few hundred words and only reallocate as necessary, kind of like we did with the int vector type, but this also will work. Words is going to be this two-dimensional array. We're allocating the first dimension. It was 0, it was empty. We're going to reallocate it. It's at least of length 1. Each of those, I should draw this out again here. Each of those is going to be a pointer to itself, potentially an array. Right? It's our pointer to a pointer here. It's a new word. We actually know how long that word is going to be, but we can keep it hard-coded that words of the current one that we just created, we can make it of that max word length. So it's a little bit of dynamic memory allocation with some hard-coded lengths. We actually know the length because we've actually already read in the word, but we can just allocate word length here. And we actually have to copy that value in. So there's our old friend string copy. Okay, there's a lot going on here. Two-dimensional array, or a pointer to a pointer, called words, as well as a separate one called word that was just a single individual word here. We need to know we've read in a valid word, our array, this outer dimension of the array is now 1 length longer. It was 0, now it's 1. We're going to reallocate it. It was 0, now it's 1. Next time around it'll be 2, then it'll be 3. That gives us that array, or that pointer is growing by length 1. Each of those is now a char star pointer to a potential array. We're actually doing 2 sets of memory allocation. One to increase the length in terms of maybe rows or number of words in our two-dimensional array here. Then we have to actually allocate space for the word itself before we try to copy it over. So we actually do a separate malloc of the individual new pointer we've just created. And it's always at the end. So we're not resizing and making the dictionary smaller and dynamically changing it. It's always growing by length 1. Num words plus plus, at least in this implementation, is always growing by 1. We're allocating 1 more word. We're then going inside that pointer we've allocated and allocating space for the actual array to store the word. Only once we've done that can we do our string copy. Probably a good time to kind of just debug. Debug that we read the dictionary. Right? Right before doing anything else, let's make sure that stuff is correct. So just confirm that for that particular file, we read it into an array. We have the dimension of the array. Words of I should be an array itself, a string corresponding to it. And okay, progress, right? We've read the entire dictionary. That is step 1 and step 2 are already done. So we haven't done anything at all with regards to sorting yet, right? There's no sorting going on here yet, but we know qsort will work for us. We just have to understand how to use qsort, and then we are really done. And any other processing we want to do with this dictionary, we've kind of actually done the hard part. We've read the whole thing into an array, a dynamically allocated array. So I guess we should probably confirm that it works for the larger dictionary, but I think it would at this point. Now we just have to understand how to use qsort. And we can sort it. And we can sort it via any kind of mechanism that is appropriate for us. This example just so happens to be sort by the length of the array. So that would be the next note I would leave for myself, that, call qsort. And the function itself is called qsort. And we know that that's not correct quite yet. I would probably then comment this block out because we don't necessarily want to print out the thing twice. And now this would be, print out sorted array. Okay, we don't have qsort sorted out yet, but anyway, that is what our qsort needs to look like. Let's look again at our definition here. Qsort's an ugly thing, right? We don't have to declare this because it's in the C standard library, but there's a prototype that looks like this. Qsort takes a pointer, takes the number of things to sort, takes the size of each of the things that we want to actually sort, and then takes that comparison function, which is going to be kind of the ugliest part here. So let's copy this down just to see what it kind of needs to look like. Oops. And let's make sure we're not actually like including that in our program. Pointer. What is the thing we want to sort? That array of words, right? We have that, it's a two-dimensional, it's a pointer to a pointer, but that is what we want to sort here. This example is going to get a little ugly, and we're going to try to follow the pointers, and maybe you'll watch me get a few sig faults and try to debug it. That is what we are sorting. Okay, so far so good. That is the pointer to the thing we want to sort. It is that array, each of which is pointing to a word. How many of them are there? There's that many. Okay, well, that's why we created that, and we have that here. How big is each of the items we're wanting to sort? That part's a little tricky. Each of those items is a pointer. It's not the array. We don't actually want to move the words themselves around. We want to reorder the pointers we have that are there. This probably needs to get drawn out for us not to go crazy with it. But it's each of those is just gonna be a pointer that we want to actually do the sorting. And then it is that final part of, okay, what is that comparison function? It is a pointer to a function that we need to then declare, which we haven't declared yet. So we just give it a name and declare it, and we're in pretty good shape there. But we have to then actually declare that function and build that function. And that's part of the syntax as well, right? Our comparison function takes as input two pointers that we're going to have to cast to what they actually are and returns an integer value. So our word comp, which is what we called ours, I guess you could say the nice thing about it is it has to look like that. And the messy thing about it is it has to look like that. So if we were to just return 0, which says that everything is kind of equal to each other, our code should compile and work. It's just not going to sort anything. If everything's equal, you're going to get the same exact result. But qsort worked. It actually did call qsort. It called this word comp function. We could say like inside word comp. And I think that's all I want to print out right now until we understand it a little bit better. And it called it a bunch of times. Didn't do anything because it returned 0. It said there's a tie each time. And let's recall this. Returns a negative integer if the first argument is less than the second. A positive integer. We're gonna need to copy paste that hint somewhere because I'm gonna keep forgetting which one is which. Okay, negative integer if the first argument is less than the second. Positive integer if the first argument is greater than the second. And if you get it backwards, just switch what you return and you're fine. It doesn't actually care what the integer is. Like you could return 1,000,000, but 1, 0, and -1 would be fine. So we're always returning 0. It thinks by our sorting mechanism that every word is equivalent. That is a type of sorting. It just doesn't change anything when we're doing the sorting. Now we got to understand what our pointers actually are here. This is a pointer to two different words that we're interested in. And A is actually going to be cast effectively as a char star. You could use the array syntax as well, but char star word A, that's the first word that we're getting pointed to that we want to compare. We don't actually know where they are in the words array, but we don't actually care. We're just being provided two addresses, and we have to interpret those as individual words. And because the whole thing is this char star star, that A is also going to be a char star star. Then we have to actually follow that pointer. That is ugly and needs a diagram. But that should work. So A is this array, two-dimensional array. B is also just a pointer inside that two-dimensional array. It's a pointer to a pointer. We're going to be doing a swap here. We then follow the first of those two pointers. And then for sanity check, we definitely need this. Are we actually getting something with our comparison? Even if we wind up returning 0 still, fine. Let's make sure it works. Okay, so you get a feel for the kind of algorithm it's doing. It's different than if we were doing bubble sort. We could probably have a little bit of fun kind of reverse engineering what algorithm it's using for the actual sorting. Is it using quicksort or some other hybrid kind of sort? But it's doing some kind of comparisons. So it is calling that word comp function, and we're getting valid strings back out via that kind of really nasty pointer following we're doing there. And the end result is still, the array didn't get changed at all because we're returning 0 every time. So we want the longer words first. So return 1 if string length of A, or what do we call it, word A, is less than string length. If I get this backwards, it's fine. It's easy enough to fix. Return 1 if string length of A is less than the string length of word B, because we want it sorted in opposite order. And if I'm wrong, that's fine. And we have that function, right? We don't have to write that ourselves. If it is, return 1. If it's not, and we should actually check for ties here, return -1. Otherwise, then if they're tied, then we return 0. And there we go. We have our sorted, very tiny little collection of words here. What was the larger dictionary called? Words alpha. There's going to be a lot of printing. This is going to print. We probably need to turn off this little debug statement to get the larger one to actually run. Look at those crazy looking words that are being printed out in the dictionary. And it's printing out the whole dictionary now, and it's quite a lot of words, and they're getting smaller and smaller as we go here. So this example does actually work. There's two tricky parts here. There's no denying it, right? So this part, it was intentionally there because we have this two-dimensional array. We're allocating in that one dimension and growing it one by one each time here. And then we still have to allocate in that second dimension each time as well. We're doing it via static length. We could have actually allocated just the right amount of characters because we now know how long the word is, but it's fine. Allocate the larger amount of data. Then we do a string copy that copies those bytes over. And then the second complexity is definitely this, qsort call here, right? And in this qsort call, part of it's okay. Words, the number of words, it's a pointer type that we're actually doing comparison of, and then we have to define that function. And for this kind of thing where it's being passed as a pointer, so we have to then follow that pointer, that's pretty nasty. Trial and error won't work, but your example you have to do for your programming practice doesn't involve pointers to pointers for this sorting function. You're sorting via integers, and you can come up with a slightly cleaner looking syntax for doing it. Let's leave things at here for this third video for this programming practice. This is the hardest programming practice of the semester that you're going to face. So do your best with it. Definitely ask for help, ask questions when you get stuck on things. These pointer problems are trickier to debug than the other kinds of logical errors you've been facing because your programs are probably going to crash when you have these errors. And let me help, and let your classmates help as well. And together we can definitely get through this example. Good luck to you.